So this will be the first lecture out of chapter 24, so the first of two lectures. So in this lecture, we'll cover amino acids, some of their basic general properties, and peptides. So some basic properties, general properties of amino acids. So you have the capacity to polymerize to form peptides and then proteins. So we'll look at their acid-base properties, and look at their chirality in this lecture. And in the next lecture, look at some of the basic reactions that they undergo. Okay, so for the amino acids, so you have a carboxylic acid, and on the alpha carbon you have an amine, and then the amino acids basically differ in what the R group, what the side chain is. So at pH of 7, amino acids exist in the Zwitter ionic form. So that's the basic structure of an amino acid. Right, you have an R group on the alpha carbon that differs. So that would be the amino acid in the non-Zwitter ionic form. But of course, amines are bases, and carboxylic acids are acids. So if we take this proton, that proton, put it on the nitrogen instead, then we would have the Zwitter ionic form of an amino acid. Where nitrogen is positive and oxygen is negative. So that's how amino acids look. So these molecules will be tautomers of each other. It's a form of tautomerization. So that's an equilibrium where they can go back and forth between each other. So it's not resonance because atoms have been moved, right? Resonance is only the movement of electrons only. In this case, you've moved an atom, you've moved a hydrogen atom from the carboxylic acid to the amine to form the Zwitter ion. Okay, so we'll look at the different classes of amino acids. So some are very hydrophobic and some are very hydrophilic. So for the hydrophobic amino acids, so they have an aliphatic, so just an alkyl group for the R group for the side chain. So you have proline, and so all amino acids have a three-letter code associated with them and a one-letter code associated with them. So proline, glycine, where the side chain is just a hydrogen, alanine, where the side chain is a methyl group, valine, where the side chain is an isopropyl group, or that would be a sec-butyl, or isobutyl, sorry, so that would be leucine, and then that would be a sec-butyl, so that would be what's called isoleucine. So three of the amino acids have an aromatic side chain. So we have phenylalanine, tyrosine, and tryptophan. And so since they have an aromatic ring, now you can do UV spectroscopy on these amino acids, or if the protein has one of these amino acids in it, then you could study that protein using UV vis spectroscopy. And so for tyrosine, we've talked about the acidities of phenols before, so that is an acidic hydrogen. Okay, so two of the amino acids, so there's 20 common amino acids, so two of them have sulfur in them. So this would be methionine with that side chain, or cysteine with that side chain. And so cysteine, of course, is acidic too. So we've talked about the acidity, so this would be a thiol, right, and this would be a sulfide in terms of their functional classes. And so thiols are more acidic than alcohols, if you remember, because just the atom size increases, the acidity increases. So cysteines are particularly important in protein chemistry because cysteines can be oxidized. So two cysteines can react with each other to make, a sulfur-sulfur bond. So you can lose the hydrogens and you can make a sulfur-sulfur bond. So that's what's called a disulfide bond. And so this will give, if it's a peptide, this will give a structure to a peptide because it'll link those two amino acids together. So some of the Amino acids have a carboxylic acid side chain, right? So a 3-carbon or a 4-carbon length, or 2-carbon or a 3-carbon length. So this is aspartic acid and glutamic acid. So since they have a carboxylic acid side chain, so they are typically deprotonated at physiological pH, and so they exist in their carboxylate form. So that would be aspartate and glutamate. And some of the amino acids have basic side chains. So we've talked about in chapter 19 that amines are bases. So in this case, with that side chain, arginine or lysine or histidine. So at physiological pH, then these can be protonated, so the amino acid can carry a net positive charge, because the Zwitter ion is a net 0 charge, right? Because the positive and negative cancels. But with one of these side chains, if protonated, then it's going to bear a net positive 1 charge. So arginine is particularly basic. It's always protonated. It's the most basic amino acid. So why is it so basic? So if you take the arginine side chain, so take a lone pair of electrons and protonate it. So this cation is particularly stable. Why is it so stable? Because of the 2 nitrogens, they can resonance delocalize that positive charge, right? You can move a lone pair down and move this double bond up. So put the positive on that nitrogen, or if you move this lone pair down there and that lone pair up, then you can put the positive charge on this nitrogen. And then you have some polar side chains that are not ionizable at physiological pH. So that would be serine with the CH2OH, so an alcohol side chain. So there's 2 with an alcohol side chain, serine and threonine. Or an amide side chain, a couple of amide side chains, asparagine and glutamine. Okay, so when these form proteins, so the amino acids with non-polar side chains, they tend to be found in the interior of a protein, which is more hydrophobic. And the amino acids with very polar side chains, they tend to be, where they're very hydrophilic, then they would tend to be on the exterior of a protein where they could interact with the aqueous environment. Okay, so some of the amino acids are essential, some are non-essential. So the essential amino acids would simply mean that one must obtain it from the diet. The non-essential amino acids can be synthesized biologically. Okay, so for stereochemistry of amino acids, so all of the 20 common amino acids are chiral except for glycine. And so let's talk a little bit about their chirality. So similar to carbohydrates, amino acids are typically classified as being L or D. So if you remember from carbohydrate, it was the OH at the last chiral center, and amino, if it was on the right, it was a D sugar. For amino acids, so if you draw the amino acid as a Fisher projection, where the carboxylic acid is on top and the side chain is on bottom, then you're left with the H and the amine and the H. And if the amine is on the right, it's a D amino acid. If the amine is on the left, it's an L amino acid. So biological systems primarily use L amino acids. So they primarily use D sugars, and they primarily use L amino acids. Okay, so the DNL is not a great way to classify the stereochemistry. It's much better to use the RNS system because DNL system, you would have to have this structure in a Fisher projection, and you would have to see where the NH2 is at in order to know if it's a D or an L amino acid. Whereas if you use the RNS system, then you can just use these simple rules to figure out the stereochemistry, right? So nitrogen's priority 1, that would be priority 2, that's priority 3. So your arrow from 1 to 2 to 3, that would be clockwise, but 4 is not vertical, it's on the horizontal. So you would reverse this arrow, right? So that would be an S amino acid. Or the way that sometimes it's taught, if you take this and if you hold the molecule in your hand such that 4 was pointing away from you, then you just draw your arrow from 1 to 2 to 3. If it's counterclockwise, it's S. If it's clockwise, it's R. but it's not necessary to do that. You can just assign R and S from a Fisher projection, right? So again, the L&D system of naming amino acids is based on carbohydrate chemistry. So this is where the L&D originated from. So D-glyceraldehyde, right? That if you drew a carbohydrate so that the aldehyde was on top and the CH2 OH on bottom, then the OH, if it's on the right, if it's D, if it's on the left, it's an L. And similarly for amino acids. So not all amino acids so L does not mean S, right? And D does not mean R. So for example, the reason why is because if you're using the RNS system of determining RNS, that is based on molar masses, right? So if we had this amino acid instead, we'll draw them up there as there's water ions, not that that matters, but just to be consistent. Ooh. So instead of serine, if this was cysteine, so for serine, this is priority 1, 2, 3, right? Because this C double bond O looks like that. So you would go to carbon and you would go to carbon, those are the same. So you would go to the next atom, and this would go to 2 hydrogens and an oxygen, whereas this carbon would go to 3 oxygens. So 1, 2, 3, that would be counterclockwise, so that would be S. 4 is on the horizontal, so you would flip it, so this would be R, right? But if this is cysteine instead, so this is still priority number 1. But then you go to carbon and carbon, those are the same. Here you go to hydrogen, hydrogen, and sulfur. Here you go to 3 oxygens, and you don't add masses up, right? You just look for the thing that has the highest mass, which is sulfur. So if your side chain is cysteine with the sulfur there, then that changes the priorities. So now this is 2 and this is 3. So now 1 to 2 to 3 is clockwise, that would be R, but this is horizontal, so you have to flip it, so it's S, right? So L does not mean S, D does not mean R. It all depends on what the priorities of the of the different groups are. But most amino acids are in the L configuration. Okay, so some of the amino acids have 2 chiral carbons, like isoleucine, for example, right? It has 2 chiral carbons. So this would be the one that's of the 20 common amino acids. So that for isoleucine, that would be the one that's predominantly used biologically. But since it has 2 chiral carbons, if you remember the formula, 2 to the 2, so 2 to the n, n's the number of chiral carbons. So isoleucine has 4 possible stereoisomers, so this just shows the other 4 possible stereoisomers. All right, these 2 are mirror images, so this is SS, this is RR, so those 2 would be enantiomers of each other. And then these 2 would be diastereomers of the L-isoleucine. Okay, so in terms of spectroscopy, so I made this point already. So phenylalanine, tryptophan, and tyrosine have a benzene ring in them, which means they can absorb UV radiation and do pi-to-pi star transitions. So you can use that if you're trying to purify a protein, for example. So you would know when protein sample was coming off of whatever instrument you're using to purify it, you could just take an UV spectrum, and when you see a signal appear, then you know the protein must be coming off of a column. Okay, so particularly for amino acids, one thing that's very important is to understand their acid-base chemistry. So this is a titration curve for alanine. So this would be alanine, right, in its neutral form, so it has no net charge. So if you drop the pH, then you can put a proton on that oxygen, and so at low pH, your amino acid is going to look like this. And then if you start increasing the pH, so you have what's called a titration curve here. So since it has, so you could deprotonate here, or you could deprotonate there, so it's got 2 acidic hydrogens. and the most acidic one is that one. So if you started increasing the pH, so if you started doing a titration and adding some base to it, then this will be the first proton that comes off. And so after that proton comes off, then you have the molecule with no net charge. And so that would be what's known as the isoelectric point. So that would be the point at which the number of positives and negatives on the amino acid are equal, so that there's no net charge. And then if you kept increasing the pH, so kept adding base, then eventually you're going to take one of the protons off of nitrogen. So then that would be the second pKa. So the first pKa is 2 and the second pKa is 10. And so Pi is just the average of those two. And so at high pH, then alanine would have a net -1 charge. So if this was glutamic acid instead, so this is the side chain, so the significance being, so this would be glutamic acid when it has no net charge. Right, so this is what our ionic form, and they cancel each other out. So if you drop the pH, you're gonna put a proton on to that oxygen. So at low pH, it has a net +1 charge. So at low pH, you're down here, it's got a net +1 charge. And then you start increasing the pH. So what's significant here is with this amino acid, you have 3 acidic hydrogens, because you have 2 carboxylic acids, right? Those are both acidic. Or you could lose a proton from the nitrogen, and it would be neutral. So 3 acidic hydrogens, which ones are going to come off first would be the 2 carboxylic acids. So now it's got three pKa values. Right, so the first proton that comes off would be coming off of here. So that has a pKa value of 2.2. And then the next, so at that point, your amino acid is neutral. So that would be the isoelectric point, is once you reach that point. And then if you keep increasing the pH, so adding more base, then the next proton that comes off is going to be that one. So that would be pKa value of 2. And then the third proton that comes off would be, so now at this point, the molecule's net -1 charged. And if you keep increasing the pH, then the third proton would come from the nitrogen. And now your molecule has a net -2 charge on it. Okay, so one more of these just to show you what it looks like if the side chain is basic instead. So if you have lysine, so lysine, we have 3 positions that could carry a proton: the carboxylic acid, the side chain nitrogen, or the alpha nitrogen. So at low pH, and then you start increasing the pH, the first proton that comes off is that one to make the carboxylate. So at low pH, since both of these nitrogens are protonated, it's doubly positive, it's a +2 charge. And you increase the pH. Once you lose the first acidic hydrogen, now it's +1 charged. And then the next proton that comes off is from here. And now you have no charge because these charges cancel each other out. And then if you increase the pH even further, then now you would take off the proton from here. So again, it's got 3 pKa values. And it would be a neutral. So at pH 7, neutral pH, this proton, or this amino acid looks like this, right? It's got a net +1 charge, so that is protonated at neutral at physiological pH. Whereas this amino acid, its Pi value, where it has no charge, is 3.15. So pH of 7 is neutral, and so anything below that, the amino acid is going to carry a net +1 charge. So at physiological pH, that's going to be positively charged. Okay, so amino acids can react with each other to make peptides. So this would be illustrating that. So if we take these 4 amino acids, so amino acids, we looked at this, amino acids and amines can react with each other, right, to lose a molecule of water. And then this nitrogen would then be attached there. So you would make an amide bond. Or in protein chemistry, that would be called a peptide bond. So of course you could do the same thing here. You could lose a molecule of water and a molecule of water, and so those 4 amino acids, you can make 3 peptide bonds. So that would be peptide bond, and that would be peptide bonds. Those are just amides, right? This is just an amide. Or if we drew this in its Zwitter ionic form, then this proton would be on that nitrogen instead. So you have the Zwitter ionic form of the peptide. So okay, so how do we name peptides? So some terminology here for you to know. So the free amino end is called the N-terminal end. So this is the N-terminal. That's the N-terminal end, and this is what's called the C-terminal end. So where you have the carboxylic acid at the end, that's the C-terminal end, or the carboxylate if you consider it in its Zwitter ionic form. Okay, so N-terminal end, C-terminal end, you should understand what those terminology means. And if you name a peptide, you name it from the N-terminal to the C-terminal end. And you would typically then use 3-letter codes for the amino acids, or the 1-letter code. Okay, so this is alanine, serine, isoleucine, phenylalanine in that sequence. So from the N-terminal to the C-terminal, so you would name it going this way. So you would name this using the 1-letter codes. You can name this A, S, I, F. So usually the letter is the first letter of the name of the amino acid, but not always, because some of the amino acids, like phenylalanine and protein, both start with P, so you can't use P, right? Or you can't use P for both, so one of them has to be different. So, but most of them have the same letter as the first letter in the name of the amino acid. Okay, so if we took these 3 amino acids and if they made a peptide, so the one that I have sketched here is we made those peptide bonds. So if we were to name this amino acid, so this is methionine, and this is alanine, and this is glycine. So this would be MAG. So that would be name of this would be MAG, right? Not GAM. GAM is a totally different protein, because that would have glycine at the N-terminal end, and then alanine, and then that would have methionine at the C-terminal end, whereas here you have methionine at the N-terminal end, and then alanine, and then glycine at the C-terminal end. Okay, so if you just have 3 amino acids, how many different proteins can you make? So I just showed you two tripeptides. So how many could you make? With those 3 amino acids, you could make 6 different proteins. So 6 different tripeptides. You can make it MAG, MGA, AMG, AGM, GAM, or GMA, right? Any sequence of those 3 different amino acids. Okay, if you had 4 amino acids, how many different tetrapeptides could you make? And the answer is a lot. You can make 24. So those are the, if you just took A, B, C, D, for example, how many ways can you rearrange those letters? You could rearrange them 24 different ways. So there's 20 common amino acids. If you just made a peptide out of 20 amino acid residues, so how many different proteins could you make? You can make a whole lot of proteins with just 20 amino acids. And of course, most proteins are more than 20 amino acids. They can be 20, 50, 100, 1,000 amino acids in sequence. Okay, we will stop there.